back to front and ask myself, are there conditions whereby the environment, in other words an ice sheet, can actually have a dominating or devastating effect on the volcano itself? And the answer is yes, very much, particularly for volcanoes that try and erupt underneath ice. And I'll illustrate it this way, very simply. This is a cross-section through an ice sheet, shown in white here, sitting on a rock. And this is supposed to be depicted at the start of an eruption where you've had hot lava passing up a crack in the Earth's crust. And when it reaches the base of the ice, of course, it causes a lot of melting. It generates a lot of meltwater from melting that ice and forms a water-filled vault. Now, you can also imagine, I think, fairly easily that if this ice is enormously thick, then the pressure at the base of that ice acting on the lava is so high that the gases which are dissolved in the lava, they can't exsolve and cause the magma to interact with the water in a vigorous way. So what happens is the lava can only come out as what we call as pillow lavas. And here's a cross-section through a pillow lava pile to show the kind of form that this kind of lava looks like. It's a very distinctive lava type, and it's caused by lava flowing into water and not able to exsolve its volatiles. Now, at this stage of the eruption, it's actually quite deeply unimpressive if you're not close to the scene. This is a view of one of those eruptions taken in 1996 in Iceland. And in this view here, the ice is approximately 700 meters thick, with enormous pressures at its base there. And there are clearly two centers in eruption at the same time. And they're forming these cauldrons on the ice surface because ice is less dense than water. If you melt it at its base, the top has to collapse to preserve the volume. So we have one center in the background here and a second center in the foreground here, and they're forming these cauldrons. Now, as the volcano continues to erupt, it gets taller and the ice above it gets thinner, therefore the pressure diminishes. As the pressure diminishes, the gases come out of the lava, they force the lava to interact with the water to much quicker. The interaction becomes quite vigorous and ultimately becomes quite violent, and the lava is shredded into tiny particles which we call ash. So in this eruption, much more vigorous interaction and a lot of ash produced, which creates deposits like this I'm showing on the right hand side here, very different from the early formed pillow lavas. Lastly, when the volcano continues to erupt and ultimately comes out the top of the ice sheet, the vent from which the lava is coming out, it dries out. There's no interaction with water, and it becomes non-explosive, and you get lava formed, which comes out of the crater, pours down the side of the volcano, and then spreads out into the ice sheet, melting its way as it goes. And all this dark material in the foreground is ash-covered ice. So at this stage, these are the kind of rocks which we form. There's lavas and other broken rocks called breccias. The names are unimportant, but all you need to know is very, very different looking from either the bedded ashes or the pillow lava that went before. So to summarize, the stage one, you have thick ice, you have non-explosive eruption and effusion of pillow lava. Stage two, thinner ice, highly explosive, very violent interaction, a lot of ashes produced. And lastly, subaerial eruption, non-explosive, superglacial, in air basically eruption and production of lavas. So to summarize it, we go from pillows to ash to lava deltas basically. And the important thing is that the products are extremely different at each stage. And I can summarize this by saying at every single stage, the environment, in other words the ice sheet, is actually telling this volcano what products it can produce and in what order. Now, the ice sheet cannot stop the eruption taking place. It can delay it, but it can't stop it. But it can definitely tell this volcano what it can produce and when. And that, although there are 9 different types of glacial volcano, this is only one of those, they all have a similar background, and this is the kind of rationale that underpins interpreting glacial volcanic sequences. So the environment is actually dictating to the volcano what it can do, when it can do it, and how it goes about it. So what information can we get from volcanoes about ice sheets? Well, first of all, it can tell us whether or not ice really was present. And clearly, if you want to talk about reconstructing a past ice sheet, you have to be able to demonstrate that ice was present when that volcano erupted. Secondly, we can determine the age of the ice by dating the radioactive elements in the lavas. This is an extremely important advantage of working with volcanic rocks. We can get very precise ages, whereas working with glacial sediments are often extremely hard to get ages from them because there's nothing in them to date directly. So it can be very hard to date glacial sediments, whereas dating volcanic lavas is very straightforward and very precise. Thirdly, and also extremely importantly, we can actually measure ice thicknesses. For any period in geological time, we can go back and say, when this volcano erupted at that time, the ice was 100 meters thick, 500 meters thick, 1,000 meters thick, plus or minus a few tens of meters. And this is the only methodology that can do that. Fourthly, if you have the ice thickness, you can then derive the relative elevation of the ice surface at the time of the eruption. And last, but by no means least, we can derive the ice thermal regime, and that's what the rest of this talk will be, the aspect we'll be talking about, I'll be talking about. So how do you determine ice thermal regime? Well, you look at the surface and see what the ice has done to it. Every eruption which finishes in lava, the lava replates the surface. It melts the ice sheet off and replates the surface. And then when the lava cools down, which probably will only take a few years, the ice then completely covers it. It reforms on top of it. And once it's reformed, the ice will interact with that lava surface, that freshly formed surface, according to its thermal regime. In other words, if it's a wet-based thermal regime, warm ice, it will be erosive and it will cause smooth surfaces like this one at the lower left and striations, scratches, or it produce lots of boulder clay, which is glacial sediments with rounded and abraded clasts. Or if it's a cold-based ice sheet, it actually is extremely protective. It's frozen to its surface, but it protects that surface. And here's a cross-section through one of these surfaces. It is not polished. There are actually tiny projections, quite delicate protections preserved on these surfaces, even though it may have had hundreds of meters of ice on top of it. Of course, volcanoes also are formed by multiple eruptions, so if you look at the surface on top of each of those eruptions and you determine the thermal regime, you can then date each of the eruptions and you can see how thermal regime developed with time. So for our project to look at the development of thermal regime in the Eastern Antarctic ice sheet, we went where the volcanoes were, of course, and that was in Victoria Land. And here's a view of a map, rather a sketch map of where the principal volcanoes are. Each of these circles is encompassing several very big, mostly shield volcanoes. They extend all the way from Adair Peninsula in the north here, all the way down to Mount Discovery in the south, a distance of some 800 kilometers. We've been visiting these volcanoes and working on them since 2005, and our last and probably final piece of work was in 2014, working in the Adair Peninsula. In the region, there are two principal types of volcanoes. The most common are large shield volcanoes, and this is a view of the coastline looking north. These are the volcanoes here. You can see they're actually really enormous volcanoes, and they stretch for many, many tens of kilometers individually. These are the commonest type of volcano. Each volcano lasted probably 1 million to 2 million years, so we get a very good record in these. We also have much smaller volcanoes. We call them monogenetic.